So one of the major applications of acetals is their use as a protecting group. And so I'd like for us to consider the problem on slide 25 in your PowerPoint notes on nucleophilic acyl addition. We see that we have both a ketone and an ester undergoing a reduction reaction in which we want to selectively reduce the less reactive carbonyl. The only way we can expect to carry this out without complication is to use an acetal protecting group. So let's go through how this works. So our substrate contains a ketone and it contains an ester. I'm going to go ahead and commit to a specific ester, so I'm going to use an ethyl ester. And I want to selectively reduce the ethyl ester to a CH2OH, a methylene alcohol. And so in the first step, we want to protect the more reactive reagent, the ketone. And we're going to do this by making a cyclic acetal. So we're going to use 1,2-ethylene diol in the presence of an acid catalyst. And as we've already seen in a previous podcast, this is going to form a selective acetal on the more reactive carbonyl. As a rule, aldehydes and ketones are much more reactive than carboxylic acids and carboxylic acid derivatives, which we're going to be studying right after spring break. And so at the conclusion of this reaction, we'll have an acetal and we will have the ester. The advantage of making this group, and I guess before I move on, I should point out that the oxygens that are incorporated in the place of where the carbonyl used to be, all those atoms come from the alcohol. I have lost an oxygen and I have lost two hydrogens in the form of H2O. And so H2O is the product that really no one talks about because it's not an organic product, but it is an important product. So this is going to be favored by increasing entropy. Now once I've formed this protected intermediate, now I can use something like lithium, aluminum hydride in the first step, and then in the second step, I'll use a very weak protic acid like water. And what this affords is the reduced product that is still protected. I could in fact use a stronger acid like HCl, and what I would do at that point is not only pick up a proton on the oxygen, I would also deprotect the acetal, which is what we're going to do eventually. So you could do a one-stop shop sort of thing if you wished. And of course, once I add a strong protic acid conditions, I will reestablish the carbonyl with the reduced ester. And so for this kind of regioselectivity, the protecting group is essential. So let's consider yet another problem. Now I'm on slide 26 in your chapter 20 notes. And so we have a 2-carbonyl functionality containing molecule, and we are going to make an acetal with the most reactive of the two. So if we take a look at this on our easel, the question is, am I going to form the acetal with the aldehyde or with the ester? The aldehyde is the most reactive carbonyl, therefore the answer is we're going to make the acetal with the aldehyde. Again, I'm just showing intermediates because I've already done the full mechanism for you guys. And of course, this is H plus to kickstart the reaction, and this will be my intermediate. Now, if we look at the next step, okay, so we've already proposed an intermediate. Now we want to open up this chain, so we would use a reagent like lithium aluminum hydride. If I use lithium aluminum hydride, LiAlH4, mechanistically I am adding hydrogen with a pair of electrons as my nucleophile. So we'll have attack, we'll break a pi bond, of course we'll have a negatively charged oxygen, and we'll have a hydrogen. Reform the carbonyl, and now this bond will break. So we have 1 carbon, 2 carbons, and a hydrogen. You want to really be careful that you don't drop any carbons when these molecules are lysed like this. Real easy for that to occur. 1, 2, 3. Of course, you'll have an O minus, but that will eventually pick up a hydrogen. A second hydride is going to come into play here. And again, once it picks up a proton, and it's important to see that once this picks up a proton, you're going to bring this back to the aldehyde. So let's do a few things here. So we have this alcohol. We have this aldehyde. We have this alcohol. Let's compare this to what we have for our intermediate on the PowerPoint slide. One, two, OH, 1, 2, 3, OH, perfect. And now in the last step, we're simply going to have an acetal be formed. You've got 2 alcohols within, and so this is simply going to be acid catalyzed. So all we need is protic acid to complete this sequence. So if we look at our intermediate, you have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So you can see the two 5-membered rings hiding in this. The only ingredient you're going to need, the only reagent you're going to need is a strong protic acid. And then you're going to get attack once. And so when we have attack once, you're going to have a tetrahydrofuran derivative. So we'll call this the carbon number 5, the anomeric carbon that will be attacked. Of course, this is carbon number 2. And so this is oxygen 1. Off of carbon 5, you are going to have an OH. You will protonate again with the protic acid. And you will get an intramolecular reformation of a carbonyl that will expel water. Of course, this has already activated the carbonyl because it's positively charged. And now we'll have nucleophilic attack again. And of course, just redraw this for a moment. A little bit of a boo-boo there. Let me straighten this out. And now we'll have 1, 2, 3. And so your former anomeric carbon is now a diether. And this is our major products. There's one other permutation of this that I'd like for us to consider. If we replace the alcohol with a thiol, we can produce a cyclic thioacetal. And these carbon-sulfur bonds are especially susceptible to being broken with the addition of rainy nickel. So rainy nickel will actually help us to ultimately convert a carbonyl to a methylene group. This accomplishes the same thing that a Clemmensen reduction does, that a Wolff-Kishner reduction does, that hydrogen and platinum will perform if the carbonyl is alpha to a benzene ring. So this is yet another alternative. Rainy nickel is especially good at cleaving carbon-sulfur bonds and also nitrogen-oxygen bonds. So this serves as a nice primer for how we use cyclic acetals and thioacetals as protecting groups in chemical synthesis.